This is dirt, ordinary red laterite clay scraped straight out of the ground outside Ouagadougou. And engineers here have figured out how to turn it into a building block that behaves almost exactly like concrete without a single bag of cement. So how do you make dirt act like concrete? Let's break it down. For decades, concrete was treated as the gold standard of real construction in Burkina Faso, the material that signaled progress, wealth, and modernity. Earthen construction, the kind of building technique Burkinabe communities had used for generations, was quietly pushed to the margins, associated with poverty rather than engineering. Even government efforts to change that perception struggled. Between 1991 and 2011, Burkina Faso ran a national program called Locomat, specifically to promote local, earth-based building materials, a serious government-backed attempt to shift the country's construction culture away from imported cement. Researchers today consider the project a technical success, but it never managed to scale, and imported cement and cinder block construction remained dominant across the country. Part of the problem was cultural, part of it was economic, but part of it was a real physical limitation. Traditional unstabilized earth blocks disintegrate when they get wet. In a region that faces increasingly violent rainy seasons, a building material that can't survive water isn't just inconvenient. It's a serious structural risk. That single weakness is exactly what engineers set out to solve. It's worth remembering what concrete actually costs a country like Burkina Faso, which produces essentially none of the raw industrial inputs needed to manufacture Portland cement domestically at scale. Every bag of cement used in a typical Burkinabe building project represents imported clinker, imported technology, and money leaving the country. The exact same dependency pattern this government has spent the last few years attacking in agriculture, energy, and transportation. If concrete could genuinely be replaced, even partially, with something made from soil already sitting under Burkinabe feet, the implications go well beyond architecture. The center of this research sits inside Institut 2YE in Ouagadougou, specifically its Laboratoire Écomatériaux et Habitats Durables, or LEMHAD, a laboratory dedicated entirely to sustainable construction materials. Working alongside researchers at Université Natsiboni in Bobo-Dioulasso and international partners in France and Luxembourg, teams led by scientists including Philbert Nshimiyimana, Adama Massan, and Seik Omar Sore have spent years testing how to stabilize compressed earth blocks using something other than Portland cement. Their answer is a class of material called Geopolymer binder. Instead of using cement, which is manufactured by heating limestone to extreme temperatures in a process responsible for roughly 8% of global carbon dioxide emissions, geopolymer binders are made by activating clay that's rich in silica and alumina with an alkaline solution. In Burkina Faso, that clay comes from kaolinite deposits found in several regions of the country, including quarries at Kamboinse, Kandarfa, Saba, Sabse, and Silogo. The clay is calcined, or heated, to convert it into a reactive material called metakaolin, then mixed with a sodium hydroxide solution. That chemical reaction creates a hardened binder that behaves in some ways like cement, holding the compressed laterite blocks together and protecting them from the exact weakness that doomed traditional earth construction: water. This isn't a single lucky discovery either. It's the product of a whole research program working through the problem systematically. Multiple published studies have specifically characterized different kalinitic clay deposits across the country to figure out which sources react best when calcined and activated, since not every patch of Burkinabe soil produces clay with the right mineral composition to form a strong geopolymer. That kind of granular, site-by-site testing is exactly the unglamorous groundwork that separates a genuine engineering breakthrough from a one-off lab curiosity that never survives contact with a real construction site. Here's where the science gets genuinely impressive. In multiple published studies out of 2IE, researchers found that compressed earth blocks stabilized with 15 to 20% geopolymer binder achieved mechanical properties comparable to blocks stabilized with 8% ordinary Portland cement, the traditional industry standard. In one study, blocks with 20% geopolymer content reached a compressive strength of 8.9 megapascals, squarely in the range needed for real structural masonry, not just decorative walls. To put that in plain terms, a material once dismissed as fit only for temporary huts is now, under controlled lab conditions, meeting the structural benchmark the construction industry treats as the baseline requirement for permanent masonry. That's the actual scientific claim hiding behind the impossible framing, and unlike a lot of viral engineering claims, this one comes with published peer-reviewed compression data behind it rather than a marketing pitch. Even more interesting, the geopolymerized blocks showed water stability that untreated earth blocks simply don't have. Physical testing showed non-stabilized blocks disintegrating when submerged, while the geopolymer stabilized samples held their integrity. That's the exact failure mode that made earthen construction feel impossible to trust for permanent buildings in the first place. And it's the failure mode this new stabilization method appears to directly solve. Compare that to what happens with unstabilized adobe or raw earth blocks in the field. Anyone who has watched a traditional mud brick wall slowly erode after a few hard rainy seasons understands why concrete won the popularity contest in the first place, even at a much higher financial and environmental cost. A block that performs like concrete structurally, insulates better thermally, and doesn't dissolve the first time a storm hits it directly attacks the single biggest reason people abandoned earthen construction to begin with. On top of that, the geopolymerized blocks actually outperform cement-stabilized blocks in one important way. Their thermal conductivity is lower, meaning buildings made from them stay cooler naturally, without needing as much mechanical air conditioning. In a country where indoor heat is a genuine daily hazard, that's not a minor side benefit. It might end up being just as important as the strength numbers. Cement production is one of the most carbon-intensive processes in the entire construction industry. One life cycle assessment focused on Burkina Faso's building sector found that for standard concrete wall materials, cement alone was responsible for over 88% of the associated carbon dioxide emissions. Every kilogram of Portland cement replaced by a locally sourced geopolymer binder is, in principle, a kilogram of imported, energy-intensive material that Burkina Faso no longer needs to manufacture abroad, ship in, and burn through in its buildings. Scale that up mentally for a second. Burkina Faso's urban population is projected to keep climbing toward and past 40% of the total population, which means the demand for new housing, schools, and public buildings is only going to grow. If even a meaningful fraction of that new construction shifts toward locally sourced, geopolymer-stabilized earth blocks instead of cement-heavy concrete, the cumulative carbon and import savings compound significantly over a decade of continuous urban growth, not just on a single showcase building. That fits neatly into a much bigger pattern playing out across Burkina Faso right now. In agriculture, in roads, in water infrastructure. The core idea, again and again, is capturing value locally, instead of paying to import something the country could theoretically produce or replace using its own land and its own labor. Cement has always been one of the most expensive imported inputs in Burkinabe construction. A locally sourced clay binder, if it can be scaled affordably, directly attacks that dependency. Now here's where we have to be honest, because this breakthrough is not yet a finished, mass-deployed alternative to concrete, and the researchers behind it are the first to say so. Producing metakaolin still requires calcining raw clay at high temperatures, a process that itself consumes real energy. Researchers openly acknowledge that geopolymer production remains energy-intensive, even if it's meaningfully less carbon-heavy than manufacturing Portland cement from scratch. This isn't a magic material that appears out of nowhere with zero energy cost. It's a genuinely better trade-off, not a perfect one. There's also the unresolved social problem that undermined the earlier Locomat program. Field studies in Ouagadougou have found that compressed earth block construction is still, paradoxically, seen by much of the population as a poor person's material, even as a growing urban elite increasingly seeks it out specifically because it's more sustainable and thermally comfortable than concrete. Researchers involved in a newer initiative called Habimo have been explicit that the barrier to scaling earth construction in Burkina Faso isn't really the engineering anymore. It's public perception, building codes, and a construction industry economically built around importing cement. You can solve the chemistry in a laboratory and still lose the fight in the marketplace if nobody wants to build their house out of something that reminds them of an old mud hut. There's a legal and regulatory gap too, one that rarely gets mentioned in the excitement around a new material. Building codes across much of West Africa were written with imported cement and steel-reinforced concrete as the default assumption. Getting geopolymer-stabilized earth block construction formally certified as safe and code-compliant for schools, hospitals, and multi-story buildings, not just single-story homes, is its own slow, bureaucratic process that has nothing to do with chemistry and everything to do with institutions catching up to the lab. So where does this actually stand right now? This is still fundamentally research stage innovation, tested and refined inside university and institute laboratories, not yet rolled out as a national construction standard, the way compressed earth block housing was briefly attempted decades ago. Some of the most tangible real-world testing has come through partnerships like the collaboration between Université Nazi-Boni and the World Food Programme, which has used these earth block research findings on actual buildings constructed in Burkina Faso, giving researchers real performance data instead of just laboratory samples. That's a meaningful and encouraging step, but it's a long way from replacing concrete at national scale. Building codes, contractor training, supply chains for calcined clay, and consumer trust would all need to shift significantly before geopolymer stabilized earth blocks became a mainstream choice for homes, schools, and public buildings across the country, rather than a promising material mostly found in research papers and pilot buildings. If Burkina Faso's broader push toward local materials and reduced import dependency continues at its current pace, this kind of research suddenly has a much more receptive political environment to scale into than it did a decade ago, when Locomat quietly stalled out. It also helps that this research isn't happening in isolation. International partners from Université de Lyon in France and Université de Toulouse have contributed to testing and characterizing these materials, alongside the Burkinabe teams, and funding from bodies like the Luxembourg Agency for Development has helped push some of this work from pure laboratory science toward applied testing on real structures. That kind of sustained, multi-year, internationally connected research effort is exactly the sort of foundation that eventually produces an industry, even if it rarely makes for a dramatic single headline moment, the way a new highway or dam opening does. Not impossible, and not magic, but genuinely difficult chemistry that Burkinabe and international researchers have spent years solving methodically, one clay sample and one compression test at a time. The core claim holds up under real published data. Laterite clay, activated with a locally producible geopolymer binder instead of imported Portland cement, can reach comparable structural strength, better thermal performance, and a substantially smaller carbon footprint, while directly fixing the water stability problem that made earlier earth construction attempts fail. What hasn't happened yet is the leap from laboratory success to a construction industry actually built around this material. That's the part worth watching closely over the next few years, because the science increasingly looks solved. The economics, the codes, and the culture around it are the real remaining obstacle, and those tend to move a lot slower than a compression test in a university lab. If there is a lesson buried in this story beyond the chemistry itself, it's that genuine technological breakthroughs in a country like Burkina Faso rarely arrive as a single dramatic announcement. They arrive as years of patient, underfunded, often unglamorous laboratory work, clay sample after clay sample, compression test after compression test, until something that once looked genuinely impossible, permanent buildings made almost entirely from the ground beneath them, starts to look like an engineering problem that's actually been solved. If you want to see how this connects to Burkina Faso's wider push for self-reliant infrastructure, the road and water videos are on your screen right now. See you there.